Now, as I brought up in a video earlier this week, we're going to talk about something called continuity, and then the opposite of continuity is discontinuous or discontinuity in functions. So make sure you've got your notes ready to go, and we're going to get started. So when we say something is continuous, what it means is that you can just take the number and plug it in. So like what we've been practicing earlier in the week. And it's exactly what you think it looks like when you graph it. It's that there's no holes, there's no gaps, there's no asymptotes. It's just a single flowing curve. It's continuous. There's no breaks. Now, lots of functions are just naturally continuous. You don't need to worry about continuity. Functions that are always continuous are going to be polynomials, exponential, logarithms, as long as we're talking about x is greater than 0, and sine and cosine. So if you see a polynomial, you just don't need to worry about whether or not it's continuous or not. So one thing is that there are different types of discontinuities, and that's what's going to be sort of going into our first question here, where we're drawing a graph with every type. There are three main types. One is going to be what's called a jump, and that means that we're going along and we stop at a point, it's got an end point, and then we start again from another. And this is when the left side of a limit is different than the right side of a limit. Now, another type of discontinuity would be something like a vertical asymptote. These are also called infinite discontinuities. So if I'm going to keep drawing my graph, vertical asymptote would be here. We have a point, and then it can come down from the same side. It's still a discontinuity because we don't have a singular flow. So this would be another type of discontinuity. And the last is a really important one. These are called a gap. And what that is you aren't going to always be able to see it. And that's just going to be, oh, we're going along, we're continuous, but there's just a little break here, and it continues. So we saw all of these types of discontinuities in our graphs with limits. Functions that have these discontinuities are rational functions. They often have asymptotes or gaps, and these are ones that can be written as a fraction. All other trig problems besides sine and cosine, which hopefully you would remember last year have a ton of vertical asymptotes or infinite discontinuities. And then the last ones are some piecewise functions. So that's the ones where they're written in separate pieces. Not all piecewise functions, but definitely some of them. Now, one thing that's helpful you'll also see as a piece of vocabulary regarding gap, is that this is also sometimes called a removable discontinuity. Because you can imagine it's possible that you could find a piece that's missing and just fill it in, and once that piece is filled in, it's continuous, versus here there's nothing to fill in because you can't draw a point at infinity, and here you can't fill this in because anything you put in here makes the function fail the vertical line test. So now that we're looking at this, you've seen the types of discontinuities, you are going to be asked if things are continuous or not. And this will often be with piecewise, because some of them are continuous and some of them aren't. So here we have a piecewise function that says that it's going to be x plus 4 if x is less than 0, and x minus 2 squared if x is greater than 0. So one thing you can do is, since these are both polynomials, we know that everything in this graph is continuous because this is a lovely, nice line. And everything in this second one is continuous because this is a parabola. So the question is, only at 0, do they have a jump? Do they meet here and then start again down here? Or are they continuous where that point is on both functions? So the way that we do this is we just ask ourselves, are the two parts, so x plus 4 and x minus 2 squared, equal at the point where they change over. So in this case, at x equals 0. If they are equal, it's continuous. So all you need to do is plug in for x and see if it's equal. So 0 plus 4 is equal to 0 minus 2 squared. 4 equals negative 2 squared. Yep. Since they are both equal, that means that f of x is continuous. And if I'm looking at the graph here, it's on the line before the intersection on the left-hand side, because x is less than 0. And then it changes over at this point and becomes part of the parabola, and this would be our graph of f of x. Now, you also might be asked if something like this is continuous. Now, it's not going to be because we see that it's rational. Now, the bigger question would be where is it not continuous? Well, it's going to be discontinuous where the denominator equals 0. Just like what we've been practicing with our limits. So in this case, it would be discontinuous at x equals 1, and so it has a discontinuity. Now, the question is if it is continuous as a piecewise function, meaning that, yeah, it can't be x equals 1, but what number could we plug in for that? So what we're looking at is a removable discontinuity. If you graph this function on your graphing calculator, you end up with seeing something that looks just like a line. But what you don't see, and what's really hard to see, is that there's actually a gap at x equals 1. And your calculator's not always going to show you this gap. And so this question is about a removable discontinuity. It's asking yourself, what could you use to fill in this point so that it is continuous? Now remember, our definition of continuous means that the function is equal to the limit. And we're looking at the discontinuous place where x equals 1. So we want to be able to plug this in. Now, f of 1 is k. That's how this is defined. It says f of x is equal to this graph except for where k is concerned, and that's going to happen at 1. So we set that equal to 1. And then the rest of f of x is this rational function. And we're going to use the skills that we were practicing earlier in this week, and we are going to use algebra to simplify that. We have polynomials, so it's going to be through factoring. So x minus 1 cancels out of the numerator and denominator. We no longer have a denominator equaling 0 problem, so we'll just plug in our value, and we get that 1 minus 1 is equal to k, so k is 0, and if k is 0, then the whole function is continuous. Let me know if you have any questions in the comments. Please nominate anything that you have questions on from the homework in the form, and if you're really stuck, please make an appointment, and I'll talk to you all later.